Hello, AP Stat students. Today we are going to do 8.1b notes. Previously, we learned what a point estimate was, and in this particular unit, we're more concerned that the point estimate is the sample proportion. It is p hat. But in the previous section, we also learned how to interpret confidence intervals and confidence levels. Today, we are going to construct a confidence interval, but before we can do that, we have to meet some conditions for constructing a confidence interval. There are three conditions. The first one is the random condition. Data should come from a well-designed random sample or a random assignment. If you don't use a random sample or random assignment, you can't infer to the population, and therefore you can establish cause and effect. However, if you have a well-designed experiment, you can still establish cause and effect. We don't want to use a volunteer sample or convenience sample, something that has bias. The second condition is the normal condition, and we were introduced to the normal condition in the previous unit. The sampling distribution of the statistic is approximately normal. When we're dealing with proportions, the normal condition for proportion is n times p is greater than or equal to 10. That n times p is known as your success. So the successes have to be greater than or equal to 10, and the failures, n times 1 minus p, also has to be greater than or equal to 10. And that only deals with the normal condition for proportions. If it's a normal condition for means, if the population is normal, then the sampling distribution will also be normal. However, if the population is not normal, then the sample size has to be large enough, and that large enough sample has to be greater than or equal to 30. And that's from the central limit theorem. We are going to learn more about means in the next unit, but where our focus is on proportions. And our last condition is our independent or 10% condition. Sampling with replacement for the population allows us to use the standard deviation formula. But if we don't sample, if sampling without replacement, we must meet the 10% condition for independence. And the 10% condition is the population size n has to be greater than or equal to 10 times the sample size, or the sample size has to be less than or equal to 10 times the population. Although sampling more than 10% will give us more precise results, we would have to use a finite population correction formula, which we try to avoid, and that's something you would use in more advanced statistics classes. In our case, we are just going to do the 10% condition. Also, here's something to note. Our method of calculation assumes a simple random sample, not a stratified or cluster sample, which again would have more complex calculations. The margin of error is only accurate if the survey or experiment is done well. Undercoverage and non-response in a sample survey can lead to additional errors, and then you would just have to start all over again. Okay, now, confidence intervals for categorical data. When given a statistics problem, we will use what is called a one-sample confidence interval for proportions when they are asking us to estimate the percentage or proportion of the population, so estimating the parameter. Once we know which inference procedure to use, we check to make sure we meet the conditions, as I stated on the previous page, to use the procedure, or else we can't use the procedure. So, conditions for estimating. This was from section 7.2 and deals with the sampling distribution of a sample proportion, so p hat. The shape, so the normal condition. The sample size is large enough so that, but here's the thing, since we don't know what p is, we don't know what the population, the parameter is, we can replace p with p hat. So n times p hat is greater than or equal to 10. and n times 1 minus p hat is greater than or equal to 10. So the number of successes and failures are each greater than 10. The center, the mean, is p. The mean of the sampling distribution is going to be the same as the mean of the population. As far as the spread, the standard deviation formula, notice how that formula has changed a little differently than what you were used to in the last unit. Because we don't know p, we can replace p with p hat. So since we don't know p with large samples, p hat will be close enough to p, so we can replace p with p hat to check the normal condition. Or I'm sorry, the 10% condition actually, or no, normal condition. So that's 10% because standard deviation is for your 10% condition. Right. And this is n is greater than or equal to 10n. This actually is normal condition because that's where we first replace the right here. Oops. Oh, I'm just messing up all over the place. So that's when we first replaced p hat for p. So let me go over here and erase that and put the normal condition. Because that statement is actually referring to this. Here we go. After we check the conditions, we move on to the calculations. So this is the part I like. So the calculation, the formula is not too difficult to use. Here's how you get the confidence interval for P, for your parameter, your population proportion. So we take the statistic, and the statistic, remember from last section, is the point estimate. So in our case, it's going to be P hat for proportion, plus or minus a margin of error. And the way to calculate the margin of error is the critical value times the standard deviation. And the statistic is just your sample proportion, or P hat. And then your margin of error, so this whole thing is your margin of error. The critical value is known as Z star, and I will explain what that is here in a second. And the standard error is the standard deviation formula. So Z star is actually the Z score for our confidence interval. And our standard error is our standard deviation of our sample data. For the standard deviation, we will use P hat for P in the standard deviation formula since we don't know P. So this is what the formula will be. So the standard deviation of our sample is equal to P hat times 1 minus P hat divided by the sample size, and then take the square root of it. This is called the standard error. SE of the sample proportion P hat. We will use this in the confidence interval for standard deviation. The critical value. Here's the critical value. We get the critical value from the standard normal curve. And if you forgot what that was, a standard normal curve has the mean of 0 and a standard deviation of 1. So if we want a confidence level of 95%, we could approximate using 2, since 95% of the data is within 2 standard deviations of the mean. And if you remember the empirical rule back in first semester, within 1 standard deviation of the mean, 68% of our data falls. And then 2 standard deviations would be 95, and 3 standard deviations would be 99.7. So that's why we can use 2 standard deviations as an estimate. It's not the exact, but you could use that. I prefer just using a calculator myself. For any other confidence level, we can use table A or you can use the calculator. I'm going to show you both just so you understand what a critical value is, where it comes from. So I'm going to sketch one for the 95% confidence level. So for a 95% confidence level, this is what the diagram would look like. Where can I draw it? I guess I could draw it right here. Okay. So here is our normal curve. It's not a very normal looking. It's hard to draw this. Okay, so here's our mean of 0, and then you have 1 standard deviations, 2 standard deviations, and so on. And here you have -1 and -2, so above and below the mean. And so 95% is 2 standard deviations. I guess I should have drawn this a little bit better. Did a poor job here. Okay. So we are going to say this is right here to here is 95%. So but what about the other 5%? Because that's how we get the critical value. So, and the z-score, if you remember from table A, it only gives you the left of the z-value. So we have 5% left over. We have 2.5% on one side, 2.5 on the other. So you have to take the remaining percent, so 100% minus 95, so you have 5%. And you divide it by 2 because the z-score is only the leftmost, and that gives you 2.5%. And you have to take that percent and change it into a decimal. So it'd be 0.025. What do you do with the 0.025? You go to table A and you find an area close to 0.025, and I am looking at that right now. And I get a z-score of exactly, because there's one in your table. If you go to table A and you go towards the very bottom, go to -1.9 and go all the way where the column is 0.06, and you see that the area in the table is 0.0250. And so the z-score, the z-star, is going to be 1.96. For 80%, you would take the remaining 20%, divide by 2, that gives you 10%. And so that's 0.10. You find an area close to 0.10, and when I look at the table, that gives me a z-star of 1.28. Now you're probably thinking, no, but it's negative. So in calculation purposes, we know that z-scores, if it's going to be negative, we're still going to only use the positive value. Just makes calculations easier, and you're allowed to do that. So disregard any kind of sign when it comes to the critical value, the z-star. Okay, now using your calculator to find the critical value is what students would rather prefer instead of using a table. So I know that my students in the past, they'd rather be given the calculator prompts and use that. So the calculator prompt is you go to your second vars. So go to second vars, just where you go to find normal CDF, and you are going to select inverse norm. And we used that in first semester. Not a lot, but we used it. So when you go to inverse norm, you are going to be given the following prompts. Oops. And of course, you have to label them. So the first thing is you have to put in the area. So this is where the 5% divided by 2 comes in. So for the area is not 5%, it's not 0.05, it's 0.025. The mean is 0 and the standard deviation is 1. That's already filled out for you. The only thing you need to put in is the area. Once you hit calculate, you will get z-star is 1.96. Okay, and for this one, take the remaining 1% divided by 2, and you get 0.5%. And as a decimal, so be really careful. Move the decimal point over 2 places to the left. Some of you make mistakes on your decimals, and you just can't make those. And so you would have inverse norm. Your area is 0.005, mean is 0, standard deviation is 1, and your z-star for a 99% confidence level is going to be 2.58. Now, I gave you the common ones. You can also memorize these. Like for 95%, it's 1.96. For 99%, it's 2.58. Of course, you might have to do one for 90%. So, and if you just memorize it, that's easy enough as well. All right. For the one sample Z interval for a population proportion, our new formula for constructing a confidence interval for the population proportion is as follows. So this is our formula. P hat plus or minus Z star, our critical value, times our standard error, which is the standard deviation of our sample data, and that would be P hat times 1 minus P hat times, or I'm sorry, over your sample size, all square rooted. Now, the standard error is on your formula sheet, but the Z star and the P hat isn't. So you're just supposed to know this is how you calculate the confidence interval. But it's not that bad. I mean, if it's talking about proportions, our statistic is P hat. If it's talking about means, it's going to be X bar. And of course, I'm not going to tell you what the critical value for means is going to be, but for proportions, it's called the Z star. This formula can only be used when the normal condition is met. And remember, that was N times P hat. Success is greater than or equal to 10, and failures are also greater than or equal to 10. Once we have calculated the confidence interval, we interpret what it means in context. We are going to do our two problems. So here's how it's laid out. So we have the 4-step process for the free response for confidence intervals for proportions. First step, state. What proportion do you want to estimate and at what confidence level? So an example, estimate the true proportion of people who have curly hair at West High School with a 90% confidence level. So in context, it'd be something like this. In the plan section, you name the procedure you are using. Our procedure is called a one sample Z interval for proportions. Okay. Then you check the 3 conditions. Condition 1, the random condition. Is it a random sample, random assignment? Condition 2, normal condition. So N times P hat greater than or equal to 10, and N times 1 minus P hat greater than or equal to 10. Last condition doesn't meet the independence condition. So sampling with replacement or sampling without replacement, use the 10% rule. So you must show how all 3 of these conditions are met. In the do section, if the conditions are met, you perform your calculations. First thing you want to do is find your sample statistics. So find that P hat, your point estimate. Next thing you want to do is use either table A or use your calculator. I prefer using a calculator to find your critical value, your Z star. Last thing you want to do then is get everything together and compute the interval. Show your work. What do I mean by showing your work? Plug in the numbers into your formula and use a calculator. That gets you full credit on a free response question. And then lastly, in your conclusion, interpret the results of your test in the context of the problem. So we are 90% confident that the interval from 0.6 to 0.72 captures the true proportion of people who have curly hair at West High School, something to that effect. And so let's go ahead and do an example. All right. Miss Smith's class took a simple random sample of 102 pennies from a jar of more than 2,000 pennies. They want to estimate the true proportion P of pennies more than 10 years old in their collection with 99% confidence. And the simple, I'm going to just get more information here, just underline some information and circle stuff. Their sample had 57 pennies, more than 10 years old in their collection, and 45 pennies whose date, that doesn't make sense, whose date was 10 years or less. So, all right, so in our state, and some of this I've laid out, and notice that you're going to do more stuff in the do portion. So in the state portion, we will estimate the true proportion of pennies in the jar that are more than 10 years old with 99% confidence. In our plan, let's state the procedure that we're going to use. So we are going to use a one sample Z interval for proportions. You'll be pros with doing anything that involves proportions after this unit. Okay, so is it a random sample? You can't just say, yes, it is. So state in context where you see it. So our sample was random. It says right there, I circled it. So simple random sample of 102 pennies. Now let's do the normal condition. And notice you don't know what P is, but you do know that quantities are given. So 57 pennies, that is your successes that are 10 years old. So 57 is greater than or equal to 10. So that is N times P hat. And you don't have to write that formula. And then the other one is 45 is also greater than or equal to 10. So that the normal condition is met. And now for the independent, so you're not replacing. So you did not sample with replacement. So you're going to have to see if the 10% condition applies. So take your sample size and multiply by 10. So there are, you don't even have to say reasonable to assume because there's 2,000 pennies and 102 times 10 is only 1,020. So there are more than 1,020 pennies in the jar. So all three conditions have been met, and now, therefore, we can do our calculations. So the first thing we want to do is find our sample statistic, our P hat. So we want to take 57 pennies were more than 10 years old out of 102. So that is 0.5588. Next thing we want to do is find Z star. And so I'm going to use inverse norm just because I want to. Of course, we already know the critical value because we had it on the previous page, but let's just write it in because remember, you want to get full credit for your work. So the area, it's 99%, so 1% divided by 2, that's 0.5, and that would be 0.005 as a decimal. Mean is 0, standard deviation is 1. And that gives us a Z star value of 2. Now, can you round? When you're doing these confidence intervals, it's pretty wise to use about 4 decimal places instead of 1 or 2, but that doesn't mean you always have to. Just kind of be consistent on what you're doing. Since my P hat was 4 decimal places, I'm just going to do everything with 4 decimal places. Okay, now that you have the P hat and the Z star, you can plug everything into your formula. So our confidence interval is our P hat plus or minus our Z star, which is 2.5758, times the standard deviation for our sample statistic. So it'd be P hat times 1 minus P hat. So 1 minus 0.5588 is 0.4412 divided by our sample size, all square rooted, of course. And then I did that and I got 0.5558, yeah, 5588, sorry, plus or minus. So I did everything under the square root. I multiplied the numerator divided by the denominator and took the square root of it, and I got, let me go ahead and put the 2.5758 first. I got 0.04916. And then I'm just going to keep going. So we have 0.5588 plus or minus, okay, I multiplied these two on the right side and I got 0.1266. And now you can take 0.5588 minus 0.1266, and that'll give you your lower bound for your interval, and then add. So when you subtract, you get 0.4322, and then our upper bound, 0.5588 plus 0.1266, is 0.6854. So it's a pretty small interval. Okay. And now we are going to interpret that confidence interval. So let's do our final step, our conclusion. We are 99% confident that the interval, you can write this in one sentence and you're done, from 0.4322 to 0.6854 captures the true proportion of pennies in the jar that are more than 10 years old. I feel like I'm in an English class today, writing so much. Okay, and our last example problem. Alcohol abuse has been described by college presidents as the number one problem on campus, and it is an important cause in death in young college adults. How common is it? A survey of 10,904 randomly selected U.S. college students collected information on drinking behavior and alcohol-related problems. The researchers defined, quote, frequent binge drinking as having 5 or more drinks in a row 3 or more times in the past 2 weeks. According to this definition, 2,486 students were classified as frequent binge drinkers. Okay, so now in our state portion, we will estimate the true proportion. So our whole goal in this confidence interval is to take our sample data and infer to the population. So we will estimate the true proportion of U.S. college students who are classified as, quote, binge drinkers with a 90% confidence. Now, in this particular problem, it didn't tell you to use a specific confidence level, and so you can choose 90 or 95. I mean, don't choose something like 80. So err on the good safe side of caution and do 90 or 95. Those are always good. When in doubt, use 95, but I wanted to use 90 for this one because we haven't done anything with 90% confidence. Okay, in our plan portion, we will use a one sample Z interval for proportions. My AP Stat students always like second semester better because it just all flows really well together and it's all laid out step by step. So it's not as bad, and I don't know, they just really liked they like these problems, but they don't like multiple choice problems for the life of them. Okay, random. It says in the problem that there were randomly selected 10,904 U.S. college students. Okay, doesn't meet the normal condition. So 2,486 students were classified as frequent binge drinkers, so the number of successes greater than or equal to 10, and then just subtract 10,904 minus 2,486, and that gives you 8,418, because you have to list both. Independent, well, we're not sampling with replacement, so just look at your 10% condition. So multiply your sample size by 10. So 10 times 10,904. And that gives you 109,040. So reasonable to assume that there are more than 109,040 U.S. college students. All right, we met our three conditions, and now we can do some calculations. The first thing, p hat, our sample statistic. So we take our number of binge drinkers, 2,486, divided by your sample size, so 10,904. Write it as a decimal. So this time I only used 3 decimal places. So again, it's kind of how I feel half the time. Just be consistent. Okay, now for the Z star. So we're going to use our inverse norm. Okay, so remember you have 10% divided by 2. So, and you can make a note of that over anywhere you want. It's not, or not, you don't have to. And then just write that as a decimal. So that would be 0.05. So the area is 0.05. Mean is 0. Standard deviation is 1. But then your calculator, that'll give you a lovely Z star value of 1.645. We have the 2 pieces of information that we need, and we can plug them into our formula. So our point estimate, our p hat, plus or minus Z star 1.645 times the standard deviation. Okay, so we have 0.228 times 1 minus 0.228, so it would be 0.772, divided by the sample size, which is 24. Oops, I'm sorry. That was the number of successes, 10,904. Take the square root of that. So I ended up doing the math. I got 0.228 plus or minus, and I'm going to skip some of this stuff. And you totally can. Just show, you definitely want to show this portion right here. And then you can do whatever you want as far as skipping other things. So plus or minus 0 times, or 0.0066. Okay, and so my lower bound interval value is 0.228 minus 0.0066, which is 0.2214. And our upper bound is 0.228 plus 0.0066. So it is 0.2346. Okay, so the reason why this interval is so much smaller than the previous one, just a little note here, why is this such a small interval? Well, the reason why it's smaller is because the sample size is large. So the big sample size makes the interval smaller and the margin of error smaller as well. So it might be something worth writing here. So the big sample size makes the interval smaller and the margin of error, so I'm just going to put ME is what we call it, smaller. All right, and now let's interpret our interval. So we are 90% confident that the interval from 0.2214 to 0.2346 captures the true proportion of U.S. college students who binge drink. And so you got your, fill, I guess, of the 4-step problem solving process for a one sample Z interval for proportions. Now for our next time notes, I'm going to show you how to find the confidence interval using a calculator. So that'll be the next lesson. And these are your notes for today. Have a great day, stat students.